Users say the server is slow. USSH in, and CPU looks normal. Memory seems fine. So what is going on? In Linux, slowness almost always reduces to one of 5 buckets: CPU, memory, disk, network, or cloud-specific limits when you are on EC2 or similar. We are going to debug it like an SRE. Measure first, isolate the bottleneck, confirm with evidence, then fix safely. In this video, we will cover a deterministic playbook, triage commands, deep dives for each resource, Syscall level proof, and cloud versus bare metal gotchas. We will use 2 mental models to avoid random guessing. First, the latency budget. When a user sends a request, time is spent in DNS resolution, TCP connect, TLS handshake, application processing, disk reads, and finally the response travels back. Think of it like a relay race. Each runner adds time, and we need to find which runner is slow. Second, the use method by Brendan Gregg. For every resource, check 3 things. Utilization, how busy is it? Saturation, is work queuing up? And errors, are things failing? We apply this to CPU, memory, disk, and network. It is like a doctor's checklist. Instead of guessing what hurts, you systematically test each organ. This avoids the random guessing that wastes hours. Phase 1, the 90-second triage. 6 commands that tell you which bucket to investigate. Command 1, uptime. It shows load average, the number of runnable plus uninterruptible tasks over 1, 5, and 15 minutes. Compare it to your CPU count. If load average is 0.45 on a 4-core machine, you are fine. If it is 24 on a 4-core box, something is badly saturated. Command 2, top. Focus on 2 numbers, %wa, which is iowait, and %sd, which is steal time. Healthy iowait is under 2%. If you see 40% iowait, your processes are waiting on disk. If steal is 25%, the hypervisor is taking CPU away from your VM, a cloud problem. Command 3, vmstat 15. Key columns. R is the run queue, B is blocked processes, SI, and so are swap in and swap out. WA is iowait, SD is steal. If R is 18 on a 4-core machine, the CPU is overloaded. If SI and so are both non-zero and rising, the system is swapping. That is a memory problem. Command 4, free-h. Focus on the available column, not free. Cache is normal and healthy. Linux uses spare RAM for file cache. If available drops below 300 megabytes and swap usage is climbing, you have a memory problem. Command 5, iostat-xc13. 2 critical columns. Await is the average time a request waits in milliseconds, and %util shows how saturated the device is. Healthy await is 1 to 2 milliseconds on NVMe. If await hits 45 and util is 99, the disk is the bottleneck. Command 6, ss-s. A socket summary. Look at time wait count. A few hundred is normal. If you see 150,000 time wait sockets, you have massive connection churn, a network or application architecture problem. CPU issues come in several flavors. Saturation means the run queue is longer than your core count. Use vmstat-p-all13 to see per core breakdown. If one core is at 100% and others are idle, you have a single-threaded bottleneck. If all cores show high percent sys, the kernel is busy, perhaps context switching or handling too many interrupts. Use pidstat-u1 to find the offending process. It is like checking who is hogging the conference room. Now, on EC2, there is a subtle trap: CPU credits. If you are running a T-family instance, like T3.medium, you earn CPU credits when idle and spend them when busy. Once credits hit 0, your CPU is throttled to baseline, often just 20% of a core. The symptoms look like sudden slowness, even though top says CPU is only at 20%. Check CloudWatch for CPU credit balance. If it is near 0, you are being throttled. The fix?
Either switch to an unlimited credit mode or resize to an M or C family instance that does not have credit limits.
Memory issues usually show up as swap storms or out-of-memory kills. Think of swap as a slow overflow parking lot. When your main lot, RAM, is full, the OS moves pages to disk. The problem is disk is 100 times slower than RAM. Check vmstat, the SI and SO columns. If SI is 120 and SO is 240, the system is actively swapping. That is terrible for latency. It means the kernel is doing read and write system calls to the swap device every time a process touches a swapped-out page. Next, check for OM events. Run dmesg pipe grep OM or journal-k-grep OM. If the kernel OM killer has been active, you will see lines showing which process was killed and how much memory it was using. To find the biggest memory consumers, use PSAUX sorted by RSS. The resident set size tells you how much physical memory each process actually uses. A common root cause is a memory leak. The process RSS keeps climbing over time. Another is simply under-provisioned memory. The fix starts with understanding whether total committed memory exceeds available physical RAM. Disk is often the hidden bottleneck. You might think modern SSDs are fast enough, but under the hood, throughput and IOPS have hard limits. Start with iostat-xc. The await column tells you how long each I/O request waited. On a healthy NVMe drive, await should be under 2 milliseconds. If you see 45 milliseconds, something is wrong. %util near 100 means the device is saturated. Think of it like a highway. Once it hits capacity, every new car has to queue. Use iotop-o to see who is doing the I/O. Maybe a backup job or a log rotation is flooding the disk. Check df-h for full file systems and df-i for exhausted nodes. A full disk with 0% free is a silent killer. Processes start failing on write system calls. On bare metal, check smart data with smartl-. Look for reallocated sectors and pending sectors. Non-zero values mean the physical drive is degrading. If the server has a RAID array, check the RAID status. A degraded RAID means one disk has failed and the array is rebuilding, which hammers I/O. On EC2, your EBS volume has provisioned IOPS and throughput caps. You can consume every IOPS you provisioned and still feel slow because the throughput cap in megabytes per second was hit. Correlate with CloudWatch metrics: volume read ops, volume write ops, and volume throughput percentage. Network problems are tricky because they can happen at any layer of the OSI stack. Start at the top, DNS. Use dig plus stats or resolvectal query to measure DNS resolution time. Healthy DNS is under 5 milliseconds on a local resolver. If it takes 200 milliseconds, every new connection is penalized before it even starts. Under the hood, that is a send system call to your resolver and a rec waiting for the response. Next, check connection state with ss-tamp. If you see many sockets stuck in syn, the remote server is not responding. Either it is down or a firewall is dropping packets. If the local listen backlog is full, new connections queue up. Use MTR to trace the path and check for packet loss and jitter at each hop. Even 1% loss at any hop inflates your P99 latency dramatically because TCP retransmits take at least one round-trip time. Check NAC level errors with ethtool-s on the interface. Look for RX dropped, TX dropped, and RX errors. Non-zero values mean frames are being dropped at the hardware layer, possibly a duplex mismatch, a bad cable, or NIC ring buffer overflow. For surgical analysis, use dump with a filter for retransmissions. Retransmits are the smoking gun of network problems. They prove packets were lost and TCP had to resend them. Sometimes you need to prove exactly where time is spent at the system call level. Start with PSAUX and look at the WCHN column. It tells you what kernel function each process is waiting in. Processes in D state, uninterruptible sleep, are stuck waiting for I/O to complete. Use strace-tt-t on a suspect process, but only briefly, because strace adds overhead. The -t flag shows how long each system call took. Look for long calls. Poll or epol_wait means the process is waiting for network data. Connect means it is trying to reach a remote host. Read and write with high latency point to disk. Futex means lock contention. Threads are waiting for each other. For a broader view, perf top shows which kernel functions are consuming the most CPU. This is a low overhead alternative to strace. Same Linux symptoms, different root causes. Let us compare what changes between cloud and bare metal. On EC2, watch for steal time, the hypervisor taking CPU cycles. Check CPU credits on T-family instances. Network performance has ceilings tied to instance type. A T3.micro gets far less bandwidth than an M5. Large. EBS volumes have IOPS and throughput caps that are invisible to Linux tools. In a physical data center, check IPMI sensor event logs for hardware warnings. Thermal throttling can cut CPU speed in half if cooling fails. A RAID rebuild after a disk failure consumes massive I/O bandwidth. NC hardware errors, CRC failures, FCS errors point to bad cables or switch ports. Check with ethtool. The key insight is your triage commands are the same, but the interpretation layer changes. Now you have identified the bottleneck. What next? Mitigate the smallest safe change first. If it is a runaway process, kill it. If swap is thrashing, add memory or tune swappiness. If disk await is high, move the hot workload or add IOPS. If the network is dropping packets, fix the cable or resize the instance. Then verify with the same triage commands. Run the before and after comparison against your latency SLO, your P95 or P99 target. Think of it as a find, fix, verify loop. You measure, you change one thing, and you measure again. Never change two variables at once. That is how you lose the evidence trail. Let us recap the entire playbook. Step 1. Use the use method to frame your investigation. Utilization, saturation, errors for CPU, memory, disk, and network. Step 2. Run the 6 triage commands. Uptime, top, vmstat, free, iostat, assess. These tell you which bucket to investigate in under 90 seconds. Step 3. Deep dive into the bottleneck bucket with targeted commands. vmstat and pidstat for CPU, dmesg and ps for memory, iotop and smarttool for disk, dig and mtr and ethtool for network. Step 4. Prove it at the Syscall level with strace or perf if needed. Step 5. Fix, verify, repeat. And always remember the cloud layer. Steal time, CPU credits, EBS caps, and instance network limits can mask the real problem. Measure first. Guess never.